Today on the Lab Report, we'll learn that heat is the transfer of thermal energy from one object to another. That the transfer of thermal energy can occur by conduction, convection, or radiation. And some materials can store more thermal energy than others. Hey, I'm Dr. Jeff, and today we're learning about heat. Adam, Caroline, check out this paper cup. Is there anything special about it?
Totally a normal cup.
Yeah, I agree.
That's because it is. Now watch what happens if I fill it up with regular water. And now, let's try to burn it. Look at that.
Oh, I thought it would burn up.
But it did not. Why do you think it didn't burn away?
Oh, it's gotta be something special about this cup.
It really is a regular paper cup. Let's pour the water out and try again. Now, let's try this again without the water. Burns up very easily.
So that means that the water inside was what stopped it from burning up.
Yes, to understand why it didn't burn with water, we first need to review thermal energy. You remember the basics of thermal energy, right?
Thermal energy describes the motion energy of molecules.
Like when you heat something up, you increase the thermal energy, which makes the atoms move faster.
And when you cool something down, you decrease the thermal energy, which makes the atoms move slower.
Yes, and heat is the transfer of thermal energy from one place to another.
So, instead of asking my mom to heat up my leftover pizza, I could say, "Hey mom, can you transfer thermal energy into my pizza?"
That sounds kind of weird, but it is correct. And there are 3 ways to heat something. We call those ways conduction, convection, and radiation. Conduction is the transfer of thermal energy through direct contact. Convection is transfer through circulating fluids, and radiation is transfer through waves.
That's a lot to take in.
It is, so let's explore them one at a time, starting with conduction. Conduction is the transfer of thermal energy through direct contact. Watch what happens when we heat this copper rod, which has 3 pieces of chocolate on it.
The thermal energy is being conducted along the rod.
And when that energy is transferred to the chocolate, it will melt and fall off.
When thermal energy is conducted along the copper rod, vibrating atoms bump into each other, causing the ones next to them to vibrate too. The result is thermal energy transfer. Now, let's repeat this demonstration with a thicker bar. What do you think will happen if we heat both of these copper rods with chocolate on them? One rod is thin and one is thick.
I think the thicker one will melt the chocolate faster. It will transfer more energy because it's bigger.
I think the thicker one will need more thermal energy to heat up, so it'll melt the chocolate slower.
Both reasonable thoughts. Let's find out.
Interesting. The thinner rod melted the chocolate faster.
That's because there are less atoms in the thinner rod, so it heats up faster.
That's exactly right. This is why when scientists compare the thermal properties of different materials, they have to keep the mass the same. I'll show you that with another example. I've heated up 3 cubes with the same mass to the same temperature using this hot plate. One cube is made of iron, another tin, and the third one is made of bismuth. Let's drop the hot cubes into the water over here and see how much the water temperature changes. Currently, all these beakers have the same amount of water at about 25 degrees Celsius. Here we go. Let's start with the iron cube. And now the tin cube. And finally, the bismuth cube.
Interesting. The iron cube heated the water to 34 degrees Celsius, the tin to 29 degrees Celsius, and the bismuth to 27 degrees Celsius.
And since they all have the same mass, this experiment shows that different metals can store different amounts of thermal energy.
Exactly. This was also an example of conduction, heating by direct contact. Thermal energy was transferred from the hot plate to the blocks, then from the blocks to the water.
And then, when the water's thermal energy increased, so did its temperature.
Yes, remember that temperature is the average kinetic energy of the atoms in a substance.
What do you mean by average kinetic energy?
How fast molecules in a substance move depends on their kinetic energy, which is motion energy. But not all the molecules in a substance move at the same speed. Some move a little faster and some move a little slower. So temperature measures the average kinetic energy of all the atoms in that substance.
So, temperature isn't just the amount of thermal energy in an object?
No, it's not. And I can show you this with a cup of tea. Thanks. Would you agree that this cup of tea and this spoonful of tea are at the same temperature?
Yes.
For sure.
Well then, would it be more painful if the whole cup spilled on you or just the spoonful?
Oh, definitely the whole cup.
Why?
Because even though they are the same temperature, the cup of tea has more thermal energy than the spoonful of tea.
That's right. Good job. Let's move on to convection. This fog machine makes fog. Notice that the fog rises up. Why do you think that is?
That's due to density, which is how closely particles are packed together.
Exactly. Heating something up makes particles spread further apart.
Which decreases the density and causes it to rise up.
Excellent. Now watch what happens if we send the fog through this box of ice. Thanks.
It cools it down, which causes the particles to pack closer together.
Which increases the density, causing it to sink.
Yes, this happens in a plain old pot of water too.
The water at the bottom is closest to the fire, so it heats up first. The particles start vibrating more and spread out, making it less dense, so it rises up.
Then, as it moves further from the heat source, it cools and becomes more dense. That makes it sink.
And that can repeat in a cycle over and over again. This process is called convection, which is the transfer of thermal energy through the circulation of a liquid or gas. We can see convection in this bowl of water by adding this special liquid to it. Now, let's turn on the heat. Perfect. As the water circulates, the crystals from the special liquid ride along the currents, allowing us to see convection.
So the same thing happens in regular water, it's just hard to see.
Exactly. Convection is also used to heat our homes.
This device along the wall heats the air. causing it to rise. Then the air cools and sinks, circulating the air in the room and heating it.
Excellent. Now let's talk about radiation. When you sit around a campfire, you can feel its warmth, even if you're not very close. That's radiation. Energy transferred through waves, mostly visible light waves and infrared light waves.
So, when waves transfer energy from the fire to our skin, the atoms in our skin start to move faster.
Another example of radiation is at a buffet. Heat lamps set above the food make infrared light waves, which heat the food without touching it.
Yes, this special light bulb is releasing a lot of radiation.
Definitely. My skin's warm and I'm not even that close.
If we focus this radiation using these reflectors, we should be able to light this match without touching it. Check it out.
Whoa, that's hot.
Actually, it's heat.
So we learned about conduction, convection, and radiation separately, but they can also happen at the same time. Think back to the first demonstration we did today.
When the fire was touching the cup, it was heated by conduction.
And when the water inside circulated due to the changing density, it was also heated by convection.
And radiation given off by the flame heated it as well. So why do you think the paper cup with water didn't burn away?
The thermal energy must have been quickly transferred from the paper cup to the water.
And water has properties that allow it to store a lot of thermal energy.
Great job.
Now, let's explore the ways we use thermal energy transfer in our everyday lives.
Jackets slow the transfer of thermal energy, which keeps us warm. Like this puffy jacket. It prevents the cold wind from blowing away the warm air close to your body. That slows down the transfer of thermal energy from your body to the atmosphere. These emergency blankets found in first aid kits use a different method to keep you warm. They reflect radiation given off by your body. Emergency blankets take up much less space, making them ideal for keeping in first aid kits. We can also use radiation to warm up food. This solar cooker uses mirrors to reflect radiation from the sun onto food. That increases its thermal energy. A clothing iron conducts thermal energy from the metal plate on its bottom to the clothing, allowing the threads to straighten out. And if you've ever seen a hot air balloon, they use a flame to heat up air. That also circulates the air in the balloon by convection, heating it up. When the air gains thermal energy, it becomes less dense, allowing the hot air balloon to rise. Once it cools back down, it comes back to the ground. If you've ever noticed hot air coming from an opening in your computer, that's because fans inside your computer transfer thermal energy from the electronics inside to the surrounding air, cooling down the electronics so they don't overheat.
Today, I'll show you how to heat a balloon without popping it. To do this, you will need 2 latex balloons, a candle, some water, and adult supervision. Make sure to avoid this activity if you have latex allergies. First, blow up a balloon and place it over the candle. It pops because heating latex causes it to melt. Now, pour water into the second balloon and then blow it up. Then, heat the part with the water in it. Amazing! This works because water can absorb a lot of the thermal energy with only small changes in temperature. Since the water absorbs the thermal energy, the latex doesn't melt. No melting, no popping. Try it yourself.
Thanks, Adam. Now let's review.
Today, we learned that heat is the transfer of thermal energy from one object to another.
That the transfer of thermal energy can occur by conduction, convection, and radiation.
And some materials can store more thermal energy than others.
Join us next time on The Lab Report. I'm Dr. Jeff.
I'm Adam.
I'm Caroline.
And remember, always question, always wonder.